For the last few years, we've all been blown away by AI that can write, code, and create images. But a huge shift is happening right now. We're moving past just language and into the physical world, teaching AI not just to talk, but to see, understand, and actually do things. So how do we get there? Let's dive into the new architectures that are making it all possible.
But this brings up a really interesting question, one that gets right to the heart of the whole problem. Why is it that the very same AI that can write a perfect sonnet or debug gnarly code still can't really do something a teenager can learn, like driving a car or just cleaning up a room? Well, the answer is baked right into its core architecture.
And this graph shows you the problem perfectly. The transformer, the architecture that powers models like GPT-4, has a critical flaw, a quadratic bottleneck. Just look at that red line shooting straight up. That's the cost in computing power. As you feed it more data, like frames from a video, the cost doesn't just go up a little, it multiplies. For text, that's fine. But for the fire hose of data that is real-time video, it's just way, way too expensive. So here's what we're going to cover. First, we'll really unpack that physical limit. Then we'll meet the new architectures built to smash right through it. We'll see how they solve for speed and memory, how they learn to, get this, tokenize the real world, and then we'll put it all together to see the hybrid system that's going to define physical AI by 2026. This brings us to a whole new generation of AI models. And the best way to think about them isn't as a single replacement for the transformer. No, think of them more like a specialized team, like the Avengers or something, where each member is an expert at one very specific job needed to interact with reality. And this whole evolution is happening at lightning speed. I mean, look at this timeline. We had Transformers kick off the whole text generation boom back in 2017. And now, it's just bam, bam, bam. A rapid-fire succession of new models, all designed for the physical world. The idea is that by 2026, all these pieces are going to click together into what we can call true physical intelligence. Okay, first up on the team is Mamba. It's a state-space model, or SSM. Think of Mamba as the team's historian, or its long-term memory. Its superpower is chewing through incredibly long sequences of data, like genomic data or hours of sensor readings, without breaking a sweat. It totally dodges the transformer's memory problem, making it the go-to specialist for long-term context. Next, we've got VL-JEPA. This one is our speed and efficiency specialist. See, instead of getting bogged down in every single pixel of a video stream, JEPA does something much smarter. It learns by predicting the abstract meaning of what's happening. It focuses on the concepts, not the tiny details, which makes it incredibly fast, perfect for real-time vision on a robot or in a self-driving car. Then there's VLA, which stands for Vision, Language, Action. So if VL-JEPA is the eyes of the operation, VLA is the hands. This is the absolutely critical piece that translates a high-level command from us, something like, hey, go clean the kitchen, into the series of precise physical movements a robot needs to actually do it.
And finally, where do all these AIs go to school? That would be Nvidia Cosmos. Think of Cosmos as a virtual gym or a hyper-realistic flight simulator for AI. It's a world foundation model that creates this incredible digital twin of our world, physics and all, letting these other AIs train for millions of hours in safety before they ever try to move a muscle in the real world.
So, we've met the team. Now let's really get into the nitty-gritty of how they actually overcome those two massive hurdles we talked about at the beginning, raw processing speed and memory. This chart just makes the difference so obvious. The transformer's complexity is quadratic. Mamba's is linear. Now, in simple terms, what that means is that as the input gets longer, the transformer starts to drown. It gets exponentially slower. Mamba, on the other hand, its processing time just scales nicely and proportionally. It's the difference between treading water and having a speedboat. Now, let's talk speed. On the left, you see the old way of doing things. Models like Diffusion get stuck in this pixel-perfect trap, trying to slowly generate every single blade of grass, every shadow. But look at JEPA on the right. Its approach is totally different. It just leaps forward by predicting the abstract idea, the concept of a ball rolling, not every single photon bouncing off it. This is a huge shift from generation to prediction. And the results are pretty stunning. VL-JEPA needs almost 3 times fewer operations than the standard models. And how? It's so clever. If you're watching a static scene where nothing important is happening, JEPA just waits. It only spins up and processes a frame when the meaning of the scene changes, like when a person walks into the frame. It just completely ignores all the redundant stuff. Okay, so we've got a handle on memory and speed. But now we hit the next big challenge. How do you control a physical body? This needs a totally new way of thinking, a way to tokenize reality itself. This is where the VLA model is just brilliant. A robot's movements are normally this messy, continuous wave of analog data. What VLA does is it compresses all that physical complexity into a clean, simple set of action tokens. It basically creates a new, simplified language for physical movement, a language an AI can understand and speak, just like it speaks in text tokens. It turns a messy physics problem into a clean language problem. And VLA pulls this off using a dual system architecture that's a lot like our own brains. You have a System 2 planner, which is slow and thoughtful. It takes the big command, clean the kitchen, and breaks it down into smaller goals. Then, a fast, reflexive System 1 expert kicks in and executes those small goals with lightning-fast motor control. It's like the difference between planning your road trip and actually steering the car around a corner. But you can't have a robot learning by just crashing into things in the real world. It would be way too slow and dangerous. That's why you need Nvidia's Cosmos. It's a simulated reality built from an insane 20 million hours of real video data. It's the ultimate training ground for these AI agents to learn and make their mistakes safely. Cosmos basically does three main things. First, it can predict what's going to happen next, like where a ball will land. Second, it can reason about physics. It has a built-in understanding that a glass will shatter if you drop it. And third, and this is the magic part, it masters transfer. It takes everything the AI learns in the simulation and makes sure it actually works in the messy, unpredictable real world. Okay, so we've met all the players on our team. Now let's put it all together and see what the future of physical AI is really going to look like. Because the most important thing to get is that the future isn't one single master model. It's a powerful, hybrid alliance. And this graphic just nails the three huge shifts that are underway. First, the output is moving from just text to real-world actions. Second, the way we compute is shifting from slow step-by-step processing to massively fast parallel prediction. And third, all this intelligence is moving from the big data centers in the cloud down to the local device itself, so a robot can think on its own 2 feet. So this gives us a really clear set of rules for building these things. It's a kind of cheat sheet. For high-level reasoning and planning, yeah, you still use a transformer. For chewing through long streams of data, you swap in Mamba. For fast, real-time eyes on the world, you deploy VL-JEPA. And to create all the training data you could ever need, you fire up Nvidia Cosmos. And this is the final picture. This is the winning stack. You can see it's this beautiful, seamless loop. Cosmos provides the endless training data. VL-JEPA acts as the eyes, handling real-time perception. And that dual system, VLA, acts as the brain and the hands, planning the strategy and controlling the final action. Each specialist does its job perfectly. And together, they create a system that's way more capable than any one model could ever hope to be. So the pieces are falling into place. The architectures are here, and they're getting faster and smarter every single day. For the first time, AI is truly learning to perceive, understand, and act in our physical world. Which leaves all of us with one final and very, very big question. What are we going to ask it to do first?